Hello, welcome to Scholar Fedu. This is our UTME prep series where we provide relatively detailed solutions and explanations to the UTME questions. And in this recording, we are looking at the UTME questions for physics for the year 2012. This is the first part of the recording. We are going to be looking at the first 25 questions. Before we continue, don't forget to subscribe to our YouTube channel, like and share our content. You can also visit our website at scholarf.com to practice UTME exam and modular quizzes for. Alright, first question is on paper type. What question paper type of physics, as indicated above, is given to you? In this recording, we are using the paper type blue. Now, this question is a very essential question, okay, because it determines how your exam will be marked. If you pick the wrong paper type, it means that your exam, the answers that you pick, are going to be marked against answers that are meant for another paper type, and that can greatly affect your results. So endeavor to check out for the paper type that you're given and choose it in if you have such a question as this. There are years where JAMB used different paper type, okay, and there are years where they simply served the same questions, and there are times when they just serve random questions to everybody. Next, in order to remove the error of parallax when taking measurements with a meter rule, the eye should be focused. It should be focused vertically downward on the markings, okay, on the markings. That is a reading on that meter rule. So you should look at that meter rule vertically downward like this. You should not be looking from one side or from one angle. You should be looking vertically downward on that marking. A load is pulled at a uniform speed along horizontal floor by a rope of 45 degrees to the floor. If the force in the rope is 1500 Newton, what is the frictional force on the load? Right, the frictional force on that load is going to be the horizontal component of this force. Okay, so in the question they said a load is put, okay, along the horizontal floor by a rope at 45 degrees to the floor. That is at 45 degrees to this floor here. The angle between that rope and the line, this parallel line, the floor, is 45 degree. Okay, the force in the rope, okay, with which the rope is being pulled, is 1500 Newton. So the question is calculate frictional force. That will be the horizontal component of this of the force, of the applied force here. So you say the frictional force is equal to F cos beta, okay, where this beta here is the angle of inclination to the horizontal. So you have the applied force as 1500 Newton times cos 45. So you have 1500 times cos 45 is 1 over root 2. These are one of the special angles that you need to know. JAMB will use angles like this: angle 30 degree, angle 45 degree, angle 60 degree, angle 90, angle 0 degree. Because the calculator they will be giving you, okay, does not have trig ratios, all this sine, cosine, and tan. So they are going to be using these trig ratios, these special angles that I just mentioned: 30, 45, 60, 90, and 0. They expect that you know the values of the sine, the cos, and the tan of these angles. So for cos 45 degrees it is 1 over root 2. For sine 45 degrees also 1 over root 2. Okay, cos 45 and sine 45, they have equal value, 1 over root 2. So excuse me, if you do 1 over root 2, you will get 0.7 something. So 1500 multiplied by 1 over root 2, that will give you 1061 Newton. That is the horizontal component of this force, and that will be the frictional force. Next, in the diagram, OT is, we are defining this value of this OT here. Now this is, we say, the diagram of a load at this point O that is pulled by a force of 8 Newton and another force of 8 Newton like this. So this here is going to be the resultant of these two forces, okay, while this T here is going to be the equilibrant, and this equilibrant is going to be equal to this resultant, but it would be of opposite sign, okay, because the direction is opposite. This is directed upward, while this OT, right, the tension here or the weight of the body, as the case may be, is directed downward. So this OT will be equal to OR. Alright, so to do this now, ROS is 8 Newton. Okay, to get the value, what I want to do here is resolve this force here in the vertical like this. Okay, I want to resolve this force in the vertical. So to resolve it in the vertical, I'll say the angle between this, I'm assuming that these two forces are perpendicular, that is QO and this SO. Those lines are perpendicular, meaning the angle between them is 90 degrees. So if I then divide it into 2, that means the angle is going to be 45, the angle will be 45. Then I'll resolve this in the horizontal. That's going to be 8 cos 45 degree. So I will now assume, I'm assuming again, and there are lots of assumptions I'm making in this question. I'm assuming again that the length of this OS is equal to the length of this OQ, meaning that as this is 8 Newton, this is also 8 Newton. So if I want to now get the resultant force, I'm going to resolve this in the vertical and resolve this as well in the vertical. Resolving one of this in the vertical is going to be 8 cos theta, and since I have two of them, then I'm going to have 2 times 8 cos theta. Cos theta, and that theta here is the angle here, which will be 45 degree. Okay, 45 degree. That is if you assume that these two are perpendicular and then you divide the angle into 2. So this will be 45. So 8 cos 45 times 2 gives us 11.3 Newton. Now if you look at the options, they are a little far, okay, but the closest in range to this value that I have is 11.3 Newton. Alright, if you have a better idea of how to go about solving this question, alright, you can contact us. You can leave it in the comment box or on our website. Next question: from the velocity time graph shown above, which of the following quantities cannot be determined? Alright, so the velocity time graph is a graph of velocity against time. Okay, now this point here, where this line here is parallel to the time axis here, is the point of uniform velocity. The point of uniform velocity. And this point here, where this line falls down like this, okay, what is happening here is that there is a decrease in the velocity. The velocity is originally 60, but at this point it fell down to what? To 0. In how many seconds? In 5 seconds. Okay, you can see that the time, okay, that it took, or the time covered, or the time that it took for that body, the time that body moved for you with uniform velocity is 20 seconds. Then for in 5 seconds it came back to rest. Okay, so the time that it took for it to decelerate to rest is 5 seconds. Okay, the difference between this time. Now, which of the following quantities cannot be determined from here? We can determine the deceleration, okay, using this point. We just take the slope of this part, okay, the slope of this, that will be the change in the velocity, alright, divided by the change in time. We can also determine the initial velocity, that is the velocity with which that body is moving in the beginning, and that is 60 meters per second. You can also determine the total distance traveled. That will be by taking the area of this shape here, okay, or we say find the area of this square. Is this a square? No, not a square. This is not a square, because this is 20 and this is 60. So find the area of this rectangle here plus the area of this triangle here. That will give us the total distance that is traveled. But we cannot get the initial acceleration here. The acceleration on a velocity time graph is the point where the graph slopes upward. Okay, the acceleration is the point where it slopes downward. So for acceleration, it should be sloping upward. And as you can see in this graph, that part is not covered here. Okay, you can't see any part on this graph where this where you have the graph sloping upward. So you cannot determine the initial acceleration. Calculate the total distance covered by a train before coming to rest if its initial speed is 30 meters per second with a constant retardation of 0.1 meters per second square. So the initial velocity, as we have from the question, the initial speed is 30 meters per second. Now, since that train came to rest, alright, it's retarded, meaning it decelerated until it came to rest. That means that the new velocity of that body, okay, of that train, its new velocity or speed is going to be 0. Okay, since it came to rest, or it came to a halt. Then the acceleration we are given as is 0.1 meters per second. Alright, now acceleration here is going to be negative, okay, because this is retardation, a decrease in velocity with time. So we have negative acceleration there. We then use our third equation of motion. V square is equal to u square plus 2as. This should be plus 2as, but why are we using minus here? Because this is negative acceleration. So we are saying v squared is equal to u squared minus 2as. Our v, the new velocity, is 0. So we have the 0 squared is equal to u squared, that's 30 squared, minus 2 times the acceleration, which is 0.1, then times the distance s, okay, times the distance. Then we have 0 is power 2 is 0 times 0, that is 0. 30 squared, 30 times 30 is 900, minus 2 times 0.1 is 0.2 seconds. Alright, now we can bring this minus 0.2 seconds to 0.2 s to this other side here. So minus 0.2 s, when it comes to this side, becomes plus 0.2 x. That we are going to have is 0 plus 0.2 x, and that will be 0.2 s is equal to 900. To then get the value of s, you are going to divide both sides by 0.2. So you have 900 divided by 0.2, and so s is equal to 4,500 meter. This is the distance that train is going to cover. Alright, with this, retardation, with this initial speed to come to rest. Next question: a car starts from rest and moves with a uniform acceleration for 30 meters per second for 20 seconds. Calculate the distance covered at the end of the motion. Alright, the car is starting from rest. That means that its initial velocity is 0. Okay, since it's not moving in the beginning. Then it moves with a uniform acceleration of 30 meters per second square. So the acceleration is 30 and the time is 20 seconds. Using our equations of motion, these are our equations of motion. Okay, the 3 equations of motion. We look at the question here is to find the distance covered at the end of the motion. So we look at, okay, which one. Now this is supposed to be A, this is not G, it should be A. Okay, it should be A, since we are not dealing with a projectile here. Now the question is, now which of these formula are we going to use? I'm looking for the distance s. If I use this formula, I don't even have the distance there, so there's no point with this one. There's no point using the formula, this formula. Yeah, yes, I do have it. I have the distance s here. However, what I have is the initial velocity. I don't know the new velocity. Alright, so if I'm going to use this formula, I have to first find the new velocity, maybe using this formula here and all of that. But this formula is, the easiest, in that I already have every other thing here. I have the initial velocity, I have the time, I have the acceleration. So I'm going to use this formula here. So I'll say, now since the body is starting from rest, u is equal to 0. If you substitute for that here, you're going to have a 0 times t. So this will become a 0. So you're now going to be left with half gt square. So we say the distance s is equal to half at square. So that will be equal to half times the acceleration, which is 30 from the question, 30 meter per second square, multiplied by the time, which is 20 seconds. But we have t square here, so this will be 20 square. 1 over 2 times 30, that is half of 30, that is 15, times 20 raised to power 2 is 20, times 20 we have 400. 15 times 400 is 600 meter. Alright, now if you look at the options that we have here, they are given in kilometer, and what we've got in here is in meter, so we need to convert this to kilometer. 1000 meter is 1 kilometer. Alright, so 6000 meter is going to be 6 kilometer. Okay, that's by dividing this by 1000, so we'll be getting 6 kilometer. Next, on gravitational field, a rocket is fired from the Earth's surface to a distant planet. By Newton's law of universal gravitation, the force F will. Alright, by Newton's law of universal gravitation, we have it that the force of attraction, okay, between two objects of matter is going to be directly proportional to their masses, the product of their masses, and inverse proportional to the square of their distance apart. Now this question is about distance. Okay, the question here is about distance. If now g is a constant, okay, g is a constant. This g here, this is the Newton's this is the equation from the Newton's law of universal gravitation. You have F is equal to g m1 m2 over r square, where this g is the universal gravitational constant. It does not vary, so this option increases as g varies is even out. Okay, is out. Also, there is a variation between the force and the distance between the objects. Okay, there's a variation. So as this rocket is fired from the Earth's surface, the distance between the rocket and the Earth's surface is increasing. The force cannot remain constant, so these two, they are out. Now the question is, now does the force increase as the distance reduces, or does it increase as the distance increase? So we now go back to this equation here, or to the statement of the formula. In that formula, the force varies inversely as the square of the mean separation, that is the distance between the two bodies. What that means, what that inverse proportionality means, is that the force increases as r reduces, or the force reduces as r increases. And if you look at this, what resonates here is that the force increases as r reduces. That means that if you look at this formula here, okay, you can see that this r is here at the denominator of the fraction. The smaller the value of this r, the bigger the value of this. What we are going to get for this is that, let's say when you have 5, okay, let's say this numerator is 5. If this r square is 2, for example, 5 over 2 is going to be 2.5. let's say that r now increases to 3, the r square increases to 3, that means we are going to have 5 over 3, which will give you 1 point something. That will be even less than what? 2.5. It means that as that r is increasing, this force F is what? Is reducing, and as this r is reducing, the force F is increasing. So you see that the force F will increase as r reduces. Next, if a freely suspended object is pulled to one side and released, it oscillates about the point of suspension because that body is going to undergo simple harmonic motion, okay, and it will be oscillating about the point of, so this is the point of suspension, okay. So this is where this pendulum bob is suspended initially. If you now pull it to this side and release it, you see that it starts going to and fro, it starts moving to and fro. This is because the acceleration of that body is directly proportional to its displacement from this point, okay. It is directly proportional to its displacement from this point here, from the point of suspension, or the point of what we call the point of equilibrium. Yeah, we have our website at scholar.com where you could practice exams for free, the UTME exam and the post-UTME exam. It also features modular quizzes in physics, chemistry and biology. So if you've studied a topic in any of the subjects and you want to test your understanding of the topic, you can head on to our website at scholar.com and take modular quizzes for free. Also, if you sign up on the website, it has a personalized dashboard where you could use to check your progress in learning. We also have interactive sessions on the website and on our social media platform. Freebies are also available to top performance on the website. Next, an object moves in a circular path of radius 0.5 meter with a speed of 1 meter per second. What is its angular velocity? Its angular velocity is given as omega, and this omega here is equal to its speed over the radius of the circular path in which the body is moving. So the speed from the question is 1 meter. So you have 1 meter divided by the radius of the circle, which is 0.5. 1 divided by 0.5 is 2 watts. So we have 2 watts per second. Okay, we have 2 watts per second. From the diagram above, calculate the work done when the particle moves from x is equal to 0 to x is equal to 80 meter. Okay, from 0 to 80 here. That's between 60 and I think this is, okay, this is 20, 40, 60, 80. So to this 80 here, to this 80. So to get the work done, we are going to take the area, okay, the area of the triangle. Okay, we take the area of the shape under this thing here. So that will be this triangle here, alright, and this triangle here. So we take the area there. So the area is going to be equal to half times the area of the triangle is half times the base times height. Half times the base times height. So the base here is from here to here. Okay, from here to here. That will be 80 minus 0 multiplied by the height. Okay, the height, which is 60 minus 0. Alright, 60 minus 0. And this will give us 1 over 2 times 80, which is 40, multiplied by 60, and this is 2400 joules. Next, the diagram above shows a wooden block just about to slide down an inclined plane, whose inclination to the horizontal is alpha. The coefficient of frictional force between the block and the plane is, the coefficient of friction, okay, is given as, is represented by this symbol here, mu, which is equal to the frictional force over the normal reaction. Now, for this body here, the frictional force F is equal to W sine theta. Okay, the frictional force holding back the body is equal to W sine theta, while the normal reaction of this block on this surface is W cos theta, or alpha. I'm using alpha here because alpha is the angle of inclination there. So you have W sine alpha, and the normal reaction is W cos alpha, where this W is the weight of this body. Now, if you substitute that into this formula here, then are going to have the frictional force W sine alpha over the normal reaction W cos alpha. W will cancel W, so you'll be left with sine alpha over cos alpha. Sine alpha over cos alpha is tan alpha. That's the trigonometric relation. An object of mass 20 kilograms slides down an inclined plane at an angle of 30 degrees to the horizontal. the coefficient of static friction is of an active friction, static friction is, alright, the coefficient of friction, just like in the previous question. Okay, we got it to be tan alpha, so here we use tan theta, where theta is going to be the angle of inclination, okay, of that body to the horizontal. So we say tan 30 degree, and that is equal to 0 points. Next, on machine, a block and tackle is used to raise a load of 250 Newton through a vertical distance of 30 meters. What is the efficiency of the system if the work done against friction is 1500 joules? We have the acceleration due to gravity as 10 meters per second. Alright, so we have the load here to be 250 Newton. The distance moved by the load is 30 meters. Okay, the efficiency of the machine is what we don't know. That's what we have to calculate. The work done against friction is given as 1500 joules. Now we look at what is the work done in lifting the load. The work done in lifting the load will be equal to the load times the distance moved by the load. That will be 250 times 30. So this is 7500. So the total work output is going to be equal to the work done against friction, which is 1500, plus the work done in lifting the load, and that is 7500 joules. So we have 9000. Then we now use the formula for efficiency. Efficiency is equal to the work output, that is the work done in lifting the load, which is 7500, over the work input, which is the sum of the work done in lifting the load and the work done against friction, that is 9000, multiplied by 100. So these two zeros will cancel out here. They have 75 divided by 90, that will be 0.83333, multiplied by 1000 by 100, and you are getting 83.3%. Next question on elasticity. If a load of 1 kilogram stretches a cord by 1.2 centimeter, what is the force constant of the cord? The force constant of the cord will be equal to the force, okay, the extension force, the force of extension, that is force that is used in extending that elastic material, divided by the extension that is produced in that material. Now in this question, the load, okay, this load is used to stretch the cord. So the force here is going to be the weight of this load that was used in stretching the cord. So we say the weight of the load is equal to the mass of the load times acceleration due to gravity. The mass of the load is 1 kilogram. We multiply that by g, and we have 1 times 10 as 10 Newton. So this is the force that is used to stretch this cord. The extension produced in the cord is 1.2 centimeter. Okay, 1.2 centimeter. We will convert this to meter by dividing this by 1000 by 100. Okay, so when you divide this by 100, we have 0.012 meter. So you can then use the formula for the force constant, that the force constant is equal to the applied force, okay, or the force causing the extension divided by the extension that it produces, and that is going to be 10 divided by 0.12 meter. So we are getting 833 Newton per meter approximately. An object of volume 1 meter cube and mass 2 kilogram is totally immersed in a liquid of density 1 kilogram. Calculate its apparent weight. Alright, the original volume of the object is 1 meter cube and the mass is 2 kilogram. Okay, now the density of the liquid in which that object was put is 1 kilogram per meter cube. Density is equal to mass over volume. Okay, the density of that object will now be the mass of the object, which is 2, divided by its volume, which is 1. So you have 2 over 1, and that is 2 kilogram per meter cube. Now the mass of the liquid that is displaced is going to be now the mass of the volume of the liquid that is displaced is equal to the volume of the object that is dipped in it. Okay, when you put an object into a liquid, the volume of that liquid that will be displaced is going to be equal to the volume of the object that you are immersing in it. Okay, so you have the volume of the liquid to also be the volume of the liquid that is displayed as 1. So the mass of the liquid displaced will now be equal to, now where did we get this from? Is from this formula here. Density is equal to mass over volume. To make mass the subject of the formula, you just cross multiply the volume. So mass is going to be density times volume. So the mass of the liquid displaced is now going to be the density of the liquid times the volume of the liquid displayed, which is equal to the liquid density. The density of the liquid is 1 kilogram per meter, multiplied by the volume of the liquid that is displayed, which is also 1 times 1, and that is 1 kilogram. The apparent weight is now going to be, now weight ordinarily is equal to mass times acceleration due to gravity, but the apparent weight is going to be the difference in the mass, okay, the difference in the mass of that object, that is the mass of the object in air minus the mass of the object in water multiplied by acceleration due to gravity, and that here is 2. This is the mass of the object in air, 2, minus its mass in the water, which is 1 kilogram, multiply that by 10. 2 minus 1 is 1. 1 times 10 is 10 newton. So this object that originally weighs, okay, that weighs like 20 newton in air is now weighing 10 newton in the water. The pressure at any point in a liquid at rest depends only on the pressure in a liquid is given as h rho g, where this h here is the depth of the liquid, the rho here means the density of the liquid, and this g is acceleration due to gravity. This is a constant value, okay, for a given location. It changes with location, but for a given location you can say it is constant on the average. So the pressure in the liquid is going to depend on the depth h and the density of that liquid. A balloon whose volume is 300 meter cube is filled with hydrogen. If the density of air is 1.3 kilogram per meter cube, find the upthrust on the balloon. Alright, the volume of the balloon, okay, is 300 meter cube. The density of air is 1.3 kilogram per meter cube. Now we recall that mass is equal to density times volume, as I explained in one of the previous questions that you came across. Mass is equal to density of volume. Alright, so you say the upthrust is also equal to the weight of, like, the apparent weight of the object in that liquid in which it was suspended. So the mass of the air that is displaced is going to be equal to rho v, okay. The mass of the object displayed is going to be the density times the volume. Remember that mass is equal to density times volume, so the mass of air that is displayed is going to be density times that is the density of the air, okay, of the air, or the gas that is used, okay, the gas that is used in filling that balloon times the volume. So we replace this mass here with density times volume. So the upthrust will now be the density, which is 1.3, the density of the air here, 1.3 kilogram per meter cube, multiplied by the volume of air, okay, or the volume of the balloon, the object that is floating in the air, which is 300, multiplied by acceleration due to gravity, that is 10. By the time we multiply all of this, we'll be getting 3,900 newton, or 39.
You can also join our online tutorial classes for different classes. We have tutorials for students in SS1, 2, or 3. We also have for UTME candidates, for JAMB candidates, for students who want to write the JAMB or the UTME exam, and for those who want to have the post-UTME exam after the UTME exam, and also for candidates that are sitting for WAEC exam or GCE or NECO. And we offer this tutorial on various platforms, so you could join us on WhatsApp or on Telegram, you could be on Zoom or on Google Classroom. So we have various platforms where we take our tutorial. The links to join the platform are available on our website at scholar.com, or you could also check it out in the video description below.
Clinical thermometers are examples of mercury in glass thermometer. Okay, mercury is a thermometric liquid that is used in clinical thermometers. Two metals P and Q are heated through the same temperature difference if the ratio of the linear expansivities of P to Q is 2:3 and the ratio of their length is 3:4 respectively. The ratio of the increase in length of P to Q is, okay, so we have two metals P and Q that are heated through the same temperature difference. That is, the change in temperature for P and for Q is the same thing, and they give us the ratio of their linear expansivity as 2:3 and the ratio of their length as 3:4. That is the original length of those metals. So we have to find the ratio of the increase in the length of the metal. Now there's not going to be an equal increase in their length. Why? Because they have different linear expansivity. Alright, so we now say the formula for linear expansivity is alpha is equal to delta L over L naught delta theta. If I want to make this change in length, the subject of the formula, I'm going to multiply this here. So I'm going to have change in length to be the linear expansivity times the original length times the change in temperature. I will now set up a ratio for the change in length of P to the change in length of Q. So I will say the change in length of P, alright, The simple way to actually do this is this. Say the change in length of P is going to be equal to the length specificity of P times the original length of P. That will be 2 times 3. Okay, so this will now be what? 6 delta theta. We are going to have 6 delta theta for this one here. Okay, why the change in length for Q is going to be the length specificity of Q times the original length of Q. That will be 3 here times 4, and that is 12 delta theta. So you have, so the ratio of the change in length of Q now to the change in length of P is now going to be 6 delta theta ratio 12 delta theta. Now delta theta means the change in their temperature, but in the question they told us that these two metals were heated through the same temperature difference. That means that the change in their temperature is the same thing. So delta theta can cancel delta theta on this side, so we are left with 6 ratio 12. Okay, I will reduce this ratio to its lowest term by dividing by 6. So if I divide by 6, I'll be having 1 ratio 2. Next question. 2000 centimeter cube of a gas is collected at 27 degrees Celsius and 700 millimeter mercury. What is the volume of the gas at standard temperature and pressure? So this is a question of volume, temperature, and pressure. So we are going to be using the general gas equation, rather, the general gas equation. All right, P1 V1 over T1 is equal to P2 V2 over T2. Where this, what you have here will be the initial values for your pressure, volume, and temperature, and this is now going to be the new value, the value at STP. All right, the value of what we have to find is the volume of the gas, that is this volume here, V2 at STP. Okay, now the initial volume of the gas is 2000 centimeter cube. The initial temperature is 27 degrees Celsius. You need to convert this to Kelvin. Always remember when you are dealing with gas laws that your temperature should be in Kelvin. So converting 27 degrees Celsius to Kelvin, we add 273, so you are having 300 Kelvin here. Okay, then the pressure, the initial pressure is 700 millimeter mercury. Now P2 and T2 are the values of the pressure and the temperature at STP, and at STP P2 pressure is 760 millimeter mercury. STP is standard temperature and pressure, while temperature at STP is 273 Kelvin. So you substitute for all of these values here, alright, and we find the value of our V2 here, the new volume. So here we have 2000 times 700 over 300 is equal to 760 times V2 over 273. You can now cross multiply. How do you cross multiply here? Just bring this here, bring this 273, bring it here, use it to, it is denominator here, use it to multiply numerator here, and use this numerator here to multiply the denominator here. So you have 2000 times 700 times 273 divided by 300 times 760. So by the time we evaluate this and divide it by what we have here, we'll be getting 1676.3158 centimeter cube, or approximately this will be 1776.3 centimeter cube. Next, on its capacity, on its calorimetry, calculate the temperature change when 500 joules of heat is applied to 100 grams of water. We have the specific heat capacity of water as 4200 joules per kilogram per Kelvin. Alright, we say that the quantity of heat supplied is equal to the mass of the body to which that it is supplied times its specific heat capacity times the change in its temperature. Now here they gave us that the quantity of heat that is supplied is 500 joules, alright, and the mass of the body is 100 gram, right? 100 gram. However, if you look at this unit for specific capacity, we have kilogram there, joules per kilogram per Kelvin, and this one is given in gram. The unit that we are using in our calculation must be balanced. So how do we balance it? Is by converting this one here to kilogram. So converting from gram to kilogram, we will divide by 1000. If you divide this 100 here by 1000, you'll be getting the 0.1, that is kilo in kilogram, 0.1 kilogram. So you solve for all of that here. The quantity of heat supplied is 500 equals the mass of the body, which is 0.1 kilogram, multiplied by the specific heat capacity of the body, that's the water here, and that is 4200 times the change in temperature. 0.1 times 4200 will give us 420. So to get the value of theta theta, I'm going to divide both sides by 420, and that will give me 1.2 degrees Celsius. Which of the following is not a factor that can increase the rate of evaporation of water in a lake? Increase in the pressure of the atmosphere. Okay, the increase in the atmospheric pressure would not affect the rate of evaporation. Factors that will affect the rate of evaporation are increase in temperature. Okay, with an increase in temperature, the rate of evaporation is faster at high temperature. Also, when you have an increase in temperature, then there will be increase in the average speed of the molecules of the water. okay, or increase in the average kinetic energy of the molecules of the water. So this is basically telling you the same thing. Rise in temperature will result into these two here, okay, but increase in pressure does not affect, atmospheric pressure does not affect the rate of evaporation. Now this does not mean that the rate of evaporation is dependent on temperature, okay. It is independent of temperature. It occurs at all temperature. However, it is faster at higher temperature. Next, the quantity of heat required to melt completely 1 kilogram of ice at minus 30 degrees Celsius is, you have the latent heat of fusion to be 3.5 times 10 raised to the power 5. The specific capacity of the ice is 2.1 times 10 raised to the power 3. Alright, we say the quantity of heat that is required is equal to the quantity of the, what's it called, the MC delta here means the mass of the body. We are dealing with ice here, okay, the mass of the ice times the specific capacity of the ice and the change in temperature plus the latent heat, okay, this is the latent heat here, the mass of the ice times the latent heat of fusion, okay. So you are going to have M is common to both of them here, so you have M in bracket C delta theta plus L, and the mass of the ice is given here as 1 kilogram, so you have 1 in bracket. Specific capacity of the ice is 2.1 times 10 raised to the power 3. Now 10 raised to the power 3 means 10 times 10 times 10, that is 1000. So this will be 2.1 times 1000, and that will be 2100. So we multiply that by the change in the temperature, okay, which is here is 30. Alright, 30 plus the latent heat of fusion of the ice. 10 raised to the power 5 means 10 times 10 times 10 times 10 times 10, and that is 100,000. 3.5 times 100,000, that will be 350,000. So by the time we multiply this and add it to this, then multiply it by 1, we'll be getting 413,000. We then write this in standard form as 4.13 times 10 raised to the power. How do I know what's going to be the power here? Since I'm posting the points here, I will count from here to the end here. So I have 1, 2, 3, 4, 5. So this will be 4.13 times 10 raised to the power 5. Alright, final question here. Which of the combinations above is correct about Brownian motion? Now Brownian motion is an example of random motion. So it is a rapid, constant and irregular motion. That is correct. It is correct. Okay, it's a random irregular motion. Next, it gives evidence that tiny particles of matter called molecules exist. Yes, Brownian motion is one of the evidences for the particulate nature of matter. It takes place only in gases is a lie. That's not correct. Okay, you also have it in other molecules, in solids as well, so in between a solid and a liquid, for example. Next, it gives evidence that molecules are in constant state of random motion. Okay, so the correct answer is I, and IV. This is also correct. Okay.
Okay, don't forget to check out our playlist. We have different playlists. We have for full solutions to UTME or JAMB questions and in physics, chemistry and biology. We also have for modular quizzes as well. Okay, we'll also have a playlist for post UTME or post JAMB exam, and also for crash courses in physics, chemistry and biology. So don't forget to check out our playlist for the available videos. So that's it for this recording. Thank you very much for watching. Please don't forget to subscribe to our YouTube channel at ScholarFedu. Okay, like and share our content, and visit our website at scholar.com to practice UTM exam and modular quizzes for free. Thank you.